Afternoon, everyone. Hope you had a good spring break and the week after that, coming back to school. So the announcement slide here is all that we have left for our class for the remaining of the semester. So first thing first, we have a slightly different schedule for this week. The speaker we have on nano extraction is currently in Korea time zone. And so I have him speaking at our Wednesday recitation slot, which is at 6 p.m. Tomorrow, Wednesday at 6 p.m. And so you can use this same class Zoom room link. We will be in this link still. And he'll be sharing his research on nano extraction and the forefront of the research frontier of that. And then we actually have two more speakers coming to our class. We have Dr. Liu speaking on water treatment and with electrolysis and things like that. And then on the 19th, we have a speaker from Bristol Myers Squibb, BMS, coming to talk about protein purification and his work in the purification team. So just an announcement for you all to remember to keep coming. We will have one last quiz on membranes, which is today's topic, and also nano extraction. And so the quiz will open tomorrow. It's short. It's meant to make sure that you have, listened to the presentation. So it's due this Friday, and it will be short. Your individual task is due this Sunday. If you have questions, this is the time to ask now. I've been fielding a lot of questions from you if your polyfit is not going correctly, or if your data is missing a lot of data points, and so the polyfit is not working correctly, and all the other problems. This is the time to ask now. And so you will have the task 3 due on May 1st, or until May 10th, if you so choose to, depending on your schedule. So keep in mind those deadlines. And then the next big assessment that we have is the task 3 for the group, which is the final presentation. They are all due next Thursday before class on Thursday, regardless of when you are actually presenting. So this is fair for everybody. Nobody gets extra time to work on their presentation. Now, I did last year have groups that came to me after the first day of presentation saying that, well, they realized that they really should change a lot of it. And so they decided to take the late penalty instead of submitting on time. So you could choose to do that, but the late penalty according to the syllabus is 20% per day. So think very carefully about that. And you are expected to attend the presentations because you will be giving your evaluations on the 19 other teams that is from the class, and that part counts towards your individual grade. You'll also need to be submitting teammates and self-evaluations by May 1st. These details are all in the PDF that is on Blackboard for this whole time. If you still have questions about the group presentation, I still have some slots available for chatting with your group this week, and some on next Monday if you really need to. So make sure to reach out to me in time so you have time to work on the final presentation and submit that by next Thursday. So that's all the announcement that I have. I'm gonna stop sharing screen here. So today we have one of our TAs, James Clark, doing the membranes presentation for us. One of the reasons why I have James in our teaching team is actually that he had a lot of experience in, I think, internships or co-ops and also research working with membranes. So I thought he would be a really great person to talk to us about the background in it, in membrane separation, as well as some of the applications that he has seen or used. So James, I am going to let you have the floor.
All right, can you hear me? See the screen?
Yes.
Great, thanks for the introduction, Dr. Josephson. So I'm James. As you know, I'm one of the TAs. Met some of you so far, but today I'm here to talk about membrane separation, which is my area of expertise. Just so you know, I'm a master's student working with Dr. Liu, who is actually going to present on electrochemical separations in a week or so. But my goal today is to give you an understanding of what membranes look like, how they work, and enough information so that you can use them in process designs. Feel free to type questions in the chat or unmute at any time if something is unclear, but yeah, thanks for having me. I'm excited to share what I've learned. So let's go. So just a little bit about me, because I think if you can realize that I'm not too different from you, maybe you'll listen a little bit more or something like that. But anyway, I graduated from Hopkins just 2 years ago. Or last year, sorry. But 2 years ago, I was right in your seat watching separations over Zoom. So I had Dr. Beatonbaugh then, and we did membrane separations for a couple of weeks. But my goal today is to hopefully distill that into just one class. And so, yeah, for my internship experience since graduating and before that, I've worked with NATL on desalination modeling and a startup called Cat's Water Technologies on just thermal desalination. And then currently I'm working with Dr. Liu on graphene oxide membranes in my master's work. Okay. Yeah, and that just summarizes what I just said. Okay, so just from a point of shared knowledge, membranes are pretty much everywhere. Even if you haven't learned about membrane separation as a unit operation before, you're certainly familiar with it. I know we've all in AP biology, high school biology, familiarized yourself with selectively permeable biological membranes, or we did this experiment with the dialysis membrane, or maybe you make coffee every morning, and or in Pebble Lab, you used vacuum filtration or Orgo Lab or something. But basically, membranes are thin, selectively permeable barriers used for filtration. Okay. And you can think about membranes as mass transfer devices in the same way that heat exchangers are heat transfer devices. Okay. Sorry. Okay, just a little bit of history. I wanted to show that membranes are a very new, young technology. The first really commercializable membranes came around for reverse osmosis desalination for drinking water in the 60s, really. And then, so it's only half a century old. And today there's huge market saturation, and there are very many large capital projects for membrane desalination, and then that's been able to fund lots of research for other applications. I'll talk about those today. And then just to show big scale, I just took this off of Amazon, but you can get a RO unit for under your sink. I don't know if you'd want to, but you can. And then you can also have just rows and rows of membrane modules. This is, I think, the Ashkelon plant in Israel, and it produces something like 100 million gallons a day of water, and like 15% of their drinking water comes from this single plant. So it really has the entire scale covered. Okay, and then for some more context, this is the ultrafiltration setup we used in senior lab. So maybe you aren't going to work on membranes in the future, but you might work on them next year. So pay attention. And this is the NETL water lab setup that I was working with data from. It's a little bit more complicated maybe than this one, but same basic principles apply. And then, yeah, finally, you can scale up. This is the Carlsbad plant in San Diego, California. It produces enough water for 400,000 people. So the scale up process I'll talk about a little bit more is how we understand the process to build these large capital products. Okay, so let's get on to today's topics. First, we're going to talk about the basic working principles. Then we are going to get into the material science a little bit. And then I'm going to talk about my experience with reverse osmosis modeling, try to explain that to you so that you can use it or at least learn something from it. And then finally, we're going to go into the other industrial applications of membrane separation. Okay. So first, continuing with general properties of membranes. I said it's a thin semi-permeable barrier used to separate solute from solvent, essentially. So we see ultrafiltration in dairy industry for whey milk separations. You can get air separation or desalination. There's lots of applications. And the different properties of the membrane confer different selectivities. And basically, based on the pore size, you can separate different compounds. So you can have a completely non-porous membrane, which is highly selective, but low flux, or you can have a very porous, macroporous. I'll show you in a second. Okay, so yeah, here is a dense non-porous membrane, which separates with diffusion and sorption, and then you actually can increase the pore size with different polymer chemistries and whatnot. This is diffusion, but size exclusion. This is diffusion, but no size exclusion. This is just convection. And these are all modeled in different ways. And on the left, you can see a very porous membrane, which has less selectivity. And then this is a thin film composite surface that is completely dense, no pores. And they have very different mass transfer models. So oftentimes we use polymeric membranes, but I'm going to also talk about different exotic membrane materials such as metals, nonmetals, and I use graphene oxide for my membranes. So, okay, so with the same figure from our textbook, the CEDAR textbook, I'll use that a lot. Some of the mass transfer concepts I talked about before, in macroporous membranes where the pore size is much larger than the molecules, there's no selectivity because there's just fast moving convection through the pores. There is a use for these macroporous membranes, which I'll talk about later, so don't forget about them, but that's how this works. And then in microporous membranes here, we can observe either selective or non-selective diffusion through the pores, which I said. And then finally, in dense membranes, we have this solution diffusion mechanism, which I will discuss in detail later on. Okay, so here is what you would get if you select for a filtration module in Aspen or something like that. It's just a block diagram, and you have one input and two outputs, let's say. So this one is called the feed. We'll have our solute and solvent, and then the product stream is the permeate, which when you pass through the membrane, you will retain the solute and then have pure solvent, and you can also have gas separations, but I'll talk about that later. And then the retentate is that concentrated stream that results from retaining the solute and pushing through the solvent. So for example, if we use seawater desalination, the feed will be, seawater is 3.5 weight% sodium chloride in water. And if you recover 50% of the water, the retentate is 7 weight% sodium chloride. And then the permeate is pretty much pure. Reverse osmosis saltwater desalination membranes are something like 99.99% rejection. So this is probably more like zero total dissolved solids. But let's just say drinking water quality is less than 500 ppm. Actually, it's so low that so below, like basically like zero, that they have to add minerals back for like health reasons for RO water. Okay, so simplifying it a little bit more to talk about the definitions, this is just our membrane here. There's a pressure on each side of the membrane. There's a consistent mass flow rate and concentrations on each side of the membrane. We can also measure the area of the membrane and the thickness. And thickness is measured using SEM images. I'll show a lot of those. So some definitions just to remind you of. Flux is very important for our large area projects. If we want to scale up, let's say a flat sheet membrane in the lab in Maryland Hall to something that can produce drinking water for 500,000 people, you have to think a lot bigger than just simple rates. So flux, you're all familiar with that. When we normalize flux by pressure, which is essentially our product versus what we can sell versus our operating costs, we get permeance. So you're dividing flux by pressure. And then when you multiply that by thickness, you get permeability. Permeability is used because you can very easily predict from like integrating Fick's law the effective thickness on diffusion. And you shouldn't report 5 or 6, 10 different permeances. You can just report one permeability. And yeah, okay. And some more definitions. We have selectivity, which is essentially the degree of separation. So we use the ratio of permeabilities. And it's similar to relative volatility in distillation or partition coefficient in extraction. And then also we can use this separation factor. And then additionally, we can also use rejection R for selectivity, essentially. That's what's used in industry. It's a very simple calculation for how much salt is going to be retained by the membrane, or how much protein is going to be retained by the membrane, how much how many cells. There are lots of applications for this. Rejection is very commonly used. Okay, so before I get deeper into modeling, I want to talk about black box models, where we don't really consider exactly what's happening at the membrane surface. We're looking at it from a like big picture perspective. Let's say we have one input, one output, isothermal, 1D, lots of assumptions, very simplified system. And we have a standard flow rate, pressure, and concentration on each side. And we are using a macroporous membrane. So large pores and convective flow. And from transport, you might remember the Hagen-Poiseuille law, and that is used to relate pressure drop to flow rate. So this is one end of the spectrum. If you have a macroporous membrane, you can relate pressure drop to flow rate very simply with something we derived when we were sophomores, right? And you can lump up this constant. We can measure all of these into permeance, and J equals P times delta P. That'll come up later on. And when we account for porosity and tortuosity, it looks a bit ugly, but you can lump these all up into a constant, and it's still the same thing over here. Just the permeance is a little bit different. So again, this is for macroporous membranes, and later on, I'm going to talk about solution diffusion through non-porous membranes, which are used for reverse osmosis. And just some cool pictures of things we've worked on. This is our setup in Maryland Hall in the basement. We have a dead end filtration cell. This is one type of lab instrument for membrane separation, where we are pressurizing a volume with water and salt and pressing it through a membrane and measuring the flux as a function of time. So this is unsteady batch, but obviously it's a lot cheaper than building this setup at NETL. But this is called crossflow, and it's steady state, which obviously adds a lot of advantages and rigor. But they're both bench scale methods of measuring, characterizing membranes. Okay, so here is actually this central flow cell in the NETL water lab. It's made by Sterilitech. Another way of saying crossflow is tangential flow, and this runs in countercurrent, if you remember from heat exchangers. We have our flat sheet membrane in the middle, screwed together, and on the top we have a feed, input and output, and this circulates along the surface of the membrane. We want it to be very well mixed so that we don't have boundary layers forming. And then on the bottom, we have something called a sweep on the permeate side. And basically the water is going to be pressed through here by hydraulic pressure through the membrane, and salt is going to be retained. So the feed output is going to have a higher concentration than the feed input. This is the retentate. And then there's going to be more water on this side of the sweep than on this side. It all moves really fast, but you measure the temperature, pressure, compositions at each of these inputs and outputs, and you can characterize the membranes. So in actuality, it functions like in a loop where we add feed to a recycle loop that is moving really fast to stir essentially on this side of the membrane, and our retentate comes out, we can measure that. Then the same thing happens on the permeate side. You can use a 1 input, 2 outputs of permeate retentate model, like I showed on the very first modeling slide. But in practice, with crossflow state-of-the-art lab setups, we will use 2 inputs and 2 outputs. And that's just a picture of what it actually looks like, the bolts and everything. All right, so I said I'd talk about scale up. Here is a different bench scale reverse osmosis setup. This is from UConn. It's Dr. Jason Arena's setup, I think, the McCutcheon lab. He was the one who built the NETL lab, not coincidentally, but they have the same flow cell and pressure gauges, conductivity meters, thermocouples, heat exchanger. And basically, with the information you gain from the bench scale, someone might want to invest in pilot skid. And here we have full membrane modules and lots of controls. And they're trying to learn what they can to scale up to a larger scale. Obviously, this is very simplified, but this is, again, the Escalon plant from another point of view. Rows and rows of these RO modules. I think the Escalon plant has 40,000 membrane modules. And you can also see, I mean, huge transmission station here. Lots of energy goes in and out, lots of water goes in and out. And then the Escalon plant quotes, I think, 0.2 cents per gallon as their overall cost for water. And then the Carlsbad plant in San Diego, which I talked about earlier, which is the largest in the US, quotes 0.5 cent per gallon. And then just to give you a little bit of a break, I know that was a lot. These are just some of the, I guess, the giants in the field of membrane separations. And if you are interested in reading more and learning a lot, these are who I would recommend you look up on Google Scholar or whatnot. UConn has a big lab, Georgia Tech, Stanford, Yale, USC, and Baker was the one who wrote the kind of fundamental text on membranes. And then obviously we have our favorite professor from chemical engineering at Hopkins, Dr. Sapatsis. He works with zeolites and absorption and gas separation. But if you're interested in membrane separations and haven't gotten a chance to take any of his classes, I definitely recommend it. And then in industry or other big names in membranes, we have NAUI is an industrial, academic, and government partnership group, and MTR is kind of like an industry, academia, research and development group. But Millipore, Dow, and DuPont are really big membrane manufacturers, and they've done a lot of development that's allowed us to have large scale desalination or ultrafiltration these days. And just to summarize, some practical considerations for membrane separation when you're trying to design a process is the molecular size and as well as properties of the target species and the other species. Also the properties of the membrane, and that works together with the properties of the molecules. So pore size, thickness, you can characterize it. Potential foulants, I haven't talked about that yet. I will get to it later. Things that can damage your membrane or affect the surface. You want to carefully consider your working concentrations for energy consumption. And you can also consider these are membrane properties, but charge and hydrophobicity. I'll talk about module design later on. And essentially, it combines a lot of different chemical engineering concepts, gets into material science, transport, process design, say thermodynamics. I'll talk about it later, but gets into everything. And then just to summarize what we've done so far, the fundamentals, we have permeance, which is P bar, they call it in the CEDAR book, or A, which is more commonly known as pressure normalized flux. And we use LMH per bar, or we can also use CGS units here. And permeability is just the thickness normalized permeance. That's always a capital P. And you can use permeance, permeability and fluxes can use mass, volume, or moles. Just be consistent and understand the assumptions involved. And then finally, selectivity and rejection determine the effectiveness of our process. Okay, so now I'm going to get into the materials, which I promised you. For the basic structure, we have two different types. We have the symmetrical membranes, which kind of were the original, but they're less effective, and then the asymmetric membranes. And kind of what birthed the membrane separation industry was the invention of asymmetric membranes in the 50s, 60s, 70s, and that development. But first, symmetrical membranes have the exact same structure throughout the entire thickness. They can have that same microporous or dense structure, but if you think about it, maybe this dense structure is very selective, but it's so thick it would take forever for something to diffuse through here. So let's say we combine the dense membrane with the microporous membrane, might be able to get something. So what we want in a membrane is mechanical stiffness so that it can withstand a high pressure, as well as the selectivity in order to add value. If we only need a very thin layer of dense membrane in order to get enough selectivity. So anything else is a waste. We shouldn't be using it as mechanical support. And what asymmetric membranes do is just that, where we use a very, very thin, dense coating on top of a porous support. The porous support adds enough mechanical support, and the dense layer doesn't subtract too much mass transfer limitation, doesn't add too much mass transfer limitation while adding a ton of selectivity. And this lobe Silurian membrane was one of the first cellulose acetate materials, one of the first anisotropic membranes. And then just some pictures of what this actually looks like. Here is a symmetric polysulfone ultrafiltration membrane. You can see it has the exact same pore structure throughout, very wide pores. These are SEM images. Here's a symmetric PES ultrafiltration membrane. This is a hollow fiber form, which I'll talk about later on, but instead of being a flat sheet, it's rolled up in a circle. It's a tube, essentially. I'll talk about it later. Here is a asymmetric composite meaning multiple materials membrane that we made a couple weeks ago. It's graphene oxide on a nylon support. And here is a polyamide industrial membrane that has 3, if not 4 layers. 3 are pictured. Very thick, thin skin of polyamide on top of a polymeric, probably polysulfone support with a PET backing. And just to summarize the materials here, we have polymeric membranes, which can take any form of these polymers here. Cellulose acetate was the beginning, polyamide is the current, and I mean, these other materials can have their purposes, but these are, if you remember too, polyamide, cellulose acetate. And then there's also inorganic membranes, which are looking to compete with the polymeric membranes because they are more resistant to fouling or thinner or whatnot. So we can use metals for gas separation. That's something that's hot these days in research. I'd say research in academia, not industry. Very expensive. Ceramics as well, aluminum, titanium dioxide, silica. We have metal organic frameworks and covalent organic frameworks. All these materials are extremely expensive. Zeolites, they have their purpose though, but it's hard to compete commercially with polymeric membranes. They're very good at what they do. And then finally, carbon nanomaterials like graphene oxide, which is what I use. So inorganic materials are very expensive, haven't really been able to compete with polymers, but have some unique properties. And a new area of research is to combine them with polymers in something called mixed matrix membranes. So while you're making the polymer, you add flakes of the inorganic material to kind of combine the best properties of both. And here are some structures of those polymers I mentioned. You can take your pick, try to beat me in the chat, but I think we have cellulose acetate here. This is polyamide, aliphatic polyamide, aromatic polyamide, and polysulfone. I'm not going to talk much about polymer science. There's entire classes about that. Okay, and then for fabrication, let's see, we can fabricate symmetric membranes pretty easily in the lab with a casting knife on top of runners. You pour out a solvent and polymer mixture or solution, and you cast it into a uniform film, let's say like this, and you just let it dry, and it'll make, it's like making paper. Then we can also make asymmetric membranes by carefully controlling the precipitation phase inversion, essentially controlling the precipitation rates at different interfaces. And you can have a thick porous support with a very thin, dense selective layer. And then composite membranes, kind of similar. You can make them a couple different ways: coating on top of a porous support, filtration on a porous support, or interfacial polymerization, kind of similar to phase inversion. Just to show you some pictures, this is a flat sheet membrane production process where we are basically precipitating a polymer solution in a coagulation bath, which is basically just water, insoluble in water. So this has some solvent putting into water, and then it has an asymmetric structure. And then this is a hollow fiber casting process where instead of casting it in thin sheets, they use this spinneret here to make an annular structure. And it looks like it's just a really long straw, essentially. And they use the same ideas of precipitation, and they carefully control every single parameter in this process, like the time it's in the air, the concentration in the spinneret, temperatures, humidities, everything to get the properties they want. Okay, and then we're about halfway through, so I figured I'd give you a break because I don't know, this is all brand new. I have some videos to show you if you want to hang around, but feel free to ask any questions at this point. Here, let's watch the hollow fiber video. So we were just looking at the process, but so here's mixing the solution, and they're going to pump it up to the spinneret I was talking about. That would be the spinneret, and they have two running. And so it's precipitating a little bit in the air and then in the water. And then they start rolling it. And they make miles and miles of this. And I'll show you how they arrange it in industrial processes. Not sure if we have one of these at Hopkins, but if we do, it would be in Dr. Sapatz's lab. Probably not this big. But yeah, that's hollow fiber spinning. So let's just take a couple minutes break. Oh, sure. Yeah, hot BA. We definitely will talk about other applications later on. Membrane separation is good for things you can't heat up. Let's say biological, like proteins you don't want to denature. They use ultrafiltration a lot because if you want to extract like solvent from a protein mixture or water or something, you can press the water out instead of using like boiling it. Also useful for low concentration mixtures. Oftentimes we combine membrane separation with distillation because each has their place. And then another pro to membranes is the modularity, which I talked about earlier. You can get a unit for under your sink or to use when you're backpacking, like pump the water out of a stream. right? But then also you can scale it up to municipal scale. I have another video. This is lab casting of a symmetric PES membrane. Just show you, and then we'll get started on the rest of the slides. So that's a polymer solution. They're rolling it out to a consistent thickness. It's still a solution. And then they're dipping it into a coagulation bath, or a non-solvent, which is water. Not so complicated. All right. So hopefully I had some time to digest in those. Oh, okay. Other question. Oh, the benefit of making annular structure. Well, I will answer this question later on. But I will say, imagine, let's say you have a flat sheet membrane like this, and you want to make as much of something as possible, but you have a limited space. If you roll up this same surface area into tiny, long, thin straws and pack them really tight together, you can get a huge amount of surface area for the same space, same volume. And that might save you costs and increase productivity. There are some concerns with hollow fibers, but yeah, they're widely used for that reason. Oh, and I could talk about the mechanism a little bit. So in a flat membrane, you're pushing solvent through, right? The same thing happens with the annular structure. You have your feed going around the structure and a pressure going in all around. You can think about heat exchangers a little bit, and you press the permeate through, and it comes out through the tube, and they're all connected at the end, and then the retentate stays along the outside. All right, I'll talk about it later, but getting into a little bit of my modeling experience with NETL, I worked with desalination, which is producing fresh water from seawater, and it's pretty common, seawater reverse osmosis, but it requires a lot of pre-treatment steps, which makes it expensive. And some of the operating parameters usually use about 50% recovery and a pressure of 50 to 80 bar. For context, the osmotic pressure of 50%, like the retentate for a 50% recovery of seawater is about 70 bar, and you need to get a little bit higher than that in order to get product, essentially. And then, yeah, you approximate seawater as 3.5% HCl in water. And then to show you what process might look like, you draw in water from the ocean, you pre-treat it to remove contaminants, fouling, like biological things that might foul the membranes, and things that the membranes might not be able to remove. Boron is one of them. And you pump that through the reverse osmosis system, and you dispose of the brine. And then the fresh water gets post-treatment, which is probably adding the minerals that we need to survive, and then pumped out to consumption. And then here we have the osmotic pressure as a function of concentration, just showing that seawater, yeah, osmotic pressure, I don't know, somewhere 50 bar range. But when you recover half of it, it gets up to here. It's there if you want to have a fit, if you ever need it. Okay, so the solution diffusion model is used to model dense membranes, and such as the ones used in reverse osmosis. Sorry. This functions using chemical potential as a universal driving force to combine pressure and concentration together. In the membrane, you have the competing forces of osmotic pressure limiting the flux and pressure pushing against it, right? You can also add electrical potential and temperature gradient in chemical potential, but for this purpose, we just use CNP. And you're familiar with Fick's law and Fourier's law and whatnot, but you can also write a phenomenological flux equation for chemical potential as the universal driving force. This is what we use for water transport, but you can actually assume just Fick's law for salt transport because the concentration term is so much larger than the pressure term. So when we integrate Fick's law for the salt flux, so Ji would be J salt. You want to account both the salt and the water transport and desalination, right? This is what results. Oh, sorry, this is not integrate. My bad, typo. We will integrate it. This is Fick's law. When you don't show the diffusion coefficient, I'll fix that. And when we account for the sorption or adsorption to the membrane surfaces and desorption off, you can use a linear isotherm, and thus adds the K term. And there's actually a lot of selectivity added from adsorption to sorption based on the affinity of the materials for the membrane. And we get this result, which looks a lot like our Hagen-Poiseuille equation from earlier. We have this lumped constant. Here, I'll show you. A times delta P, but then we also have this delta pi term, which is the concentration term. And so delta P minus delta pi acts as the chemical potential, but it's technically not in those units because we have these constants. And then salt flux just comes straight from integrating Fick's law. And yeah, that's the B that goes there. So I'll show you, when you simplify it, the A times delta P minus delta pi, that is the quintessential RO equation. And then we have B delta C for salt flux. And these are pretty effective at modeling low salinity reverse osmosis processes. The pressure is applied, yeah, I said earlier, to overcome osmotic pressure, and I said that as well. And these are from Baker's text, as well as a paper from a while back, just comparing the pore flow model, which I showed earlier, to solution diffusion. Well, pore flow model is actually just a competing model for desalination, but same concepts. Okay, so we characterize our system using A and B as constants, but how might we measure them? And this was subject of a lot of my work with NETL. I was just analyzing some data they collected in LabVIEW on their system and finding A and B. So A, like we said before, is the pure water permeability. It's found from flux tests. And basically, if you run pure water through that cross flow setup, you can vary the pressure and see the difference in the flux. And you can directly relate the delta pi cancels out because there's no salt, A delta P to JW. And that gives you this linear correlation, and the slope is A. For B, it's a little bit more complicated, but since we know A, we can do more flux tests with varying concentrations, and we can regress that data with the A we already know to get B. And I was trying to fit, this isn't exactly a linear for B delta C versus JS, but it's actually comparing experimental fluxes they measured with conductivity meters to what we predict from the equation. But it's the same idea. We used chi-squared minimization as our error, not least squares. That's similar. And now I want to talk about another important concept for reverse osmosis called concentration polarization. Now, this is a schematic of what a membrane process looks like if you think about it in the cross section. This is our membrane here, has multiple layers like we discussed earlier. The porous support, the thin active layer, the water is getting pushed across, and then also some salt is going to go with it. And this is a bit extra. You can use this to model any osmotic process, but if we simplify it a little bit, we can just look at the feed side, because in reverse osmosis, the sweep side is essentially zero, TDS, zero concentration. And basically what happens is as you push water across the membrane and retain salt, no matter what you do, salt is going to build up at the membrane surface. And that causes the boundary layer, which we call concentration polarization. And concentration polarization will decrease our driving force because this will increase the delta pi, the osmotic pressure difference across the membrane, which, since it's delta P minus delta pi, will inhibit our flux. And so modeling this correctly is very important for getting an accurate economic analysis of how much it's going to cost to run the system. So we have our basic flux equations, but actually these are interfacial differences, and we didn't account for that yet. So we can't measure this, right? Can't measure it in absorption, can't measure it here. We need a correlation or some expression. So this concentration polarization expression is derived from a convection diffusion model of the system. Basically, you're pushing convection this way, diffusing back, but convection is much larger than that diffusion, and it forms this boundary layer. And this does a good job of approximating this. And I'll talk about the parameters in just a second. Okay, so we have our same system, our three equations now, and we have three unknowns, A, B, and CFM. Now, if we assume CSM and pi SM to be 0, and we just only need three equations. But if this is not 0, then we can get a fourth correlation for the sweep side. And anyway, the diffusion coefficient is known, right? We can measure that as a function of temperature and concentration, or estimate it to be this. And then del F is the thickness of the boundary layer, if you remember that from transport. You can correlate that to the flow conditions. There's correlations in textbooks, or you can fit it to experimental data, or you can estimate it. It's not too sensitive. And then, yeah, equation 3, like I said, is boundary layer theory. And we'll go through that. Okay. So that was a discussion of how you might model a osmotic process in mathematically. The models I used were a little bit more complicated than that, but you could definitely get by with this. There are lots of different ways to do it. But if you're more interested, I'd be happy to talk to you and share more. But now let's get into the industrial applications. I'm going to talk about all those different processes you were wondering about. So here are some other filtration processes like reverse osmosis that use different pore sizes, like we talked about earlier on. There's ultrafiltration, microfiltration, nanofiltration that all just push solvent and maybe solute through a membrane and retain something. You can see in this figure here, different membranes retain different things. So microfiltration has the largest pore sizes. They only retain large colloids. And ultrafiltration is used commonly to separate proteins. Nanofiltration is kind of in between UF and RO. And it's interesting to model because it's in between. And then RO only really retains, retains everything and only passes through water. And I talked about this before. And here is just a scaled up version of ultrafiltration in the dairy industry. Also used for protein purification, which not exactly what we did here. This is from senior lab from a little more than a year ago. We were separating dextran from a dye, I believe. So large polymer from a dye molecule. And we used an ultrafiltration, I think hollow fiber membrane here in a tangential flow setup. It's a pretty cool project. I hope you guys got to do it. And for some other osmotically driven processes than reverse osmosis, here is just a schematic of the interplay between osmotic pressure, solvent concentration, and the membrane. This is actually pretty bad because I don't think there should be red on both sides. Anyway, I think you've seen these manometer pictures before. There's forward osmosis, which is exactly what it sounds like. There's lots of words here, but forward osmosis is just follows the driving force of the water goes to the saltier side to dilute it. This is commonly used in industry to for separations pre-treatment. PRO is an energy generation process. Basically, if you use forward osmosis, but you push against the water that wants to go through it, let's say you have salt on this side, water on this side. Water wants to go through, but if you push against it, or like spinning a turbine, you can generate power. BWRO is basically just high flux RO for lower salinity waters. That's used to produce drinking water out of aquifers and whatnot. Osmotically assisted RO is kind of a combination of forward osmosis and reverse osmosis. It's the big topic of the research at NETL that I was working with. High pressure RO is exactly what it sounds like. Same with low salt rejection RO. These are all just kind of new ideas in the field. Essentially the same system, but with different parameters, and then we get different results. So another different application of membrane separation is per-evaporation. And it's different from, well, it stands for perm-selective evaporation. It's different from reverse osmosis or gas permeation because it has two different phases. There's a liquid on the feed side and a vapor on the permeate side. And so you use a vacuum or heating, as well as a unique membrane to get that kind of separation. And its applications are dehydration of organics and separation of close boiling mixtures. And here's a process design of using per-evaporation to separate an ethanol water azeotrope from the CEDAR text. This isn't really used in industry, but I mean, you guys know how hard it is to separate ethanol and water above 80 weight percent. Or 80 mole percent. yeah. But they use desiccants in industry. And okay, so here's another membrane separation process that I'm sure Dr. Liu will talk about. I don't want to talk about it too much, but it's called electrodialysis, and I'll just introduce it for her. But basically, electrodialysis uses the driving force of electric potential to separate charged species out of a brine using the electric field. And a key unit of electrodialysis is a ion selective membrane, CEM or AEM. And they arrange these in series, apply a potential to both sides. And I'll show you a picture, but basically you feed it in the water and the positive and negative charges will migrate based on the electric field, and you produce fresh water and a brine in alternating forms. It looks a lot like a fuel cell. And obviously cation anion exchange membranes are useful in fuel cells as well. So here's a little picture of what that looks like. You apply an electric field across this whole system, and you can push the ions out and retain them with the ion exchange membrane. So see the negative ions can't get through the cation exchange membrane. And then also, this is just 3 channels, but they actually have lots of channels arranged in series. So there would be negative ions going through here, and then more going down there. Another application for membrane separation is called gas permeation. I remember spending like a week on this in undergrad separations with Beatenball, but there's some good resources out there. So this is the oldest membrane separation process. I think they used it in Manhattan Project to separate uranium hexafluoride, different isotopes of uranium. And it is the pressure-driven separations, the vapor phase with a membrane. And just like liquid separations, there's lots of different pore sizes, can be solution diffusion to convective, and they're separated by different properties. The applications of gas permeation are very wide, from air purification, oxygen, nitrogen, to in like fertilizer processes, I guess, hydrogen, nitrogen separation, and then hydrocarbons. It's a growing field, and there's certainly a lot of investment in gas separation. So we'll see how that comes. You'll see this is from this is from Baker's text, which I mentioned earlier, but I think there's figures just like this in the CEDAR textbook. It looks just like that 1 input, 2 output model I showed very early on. We have feed, retentate, permeate. We use partial pressures instead of concentrations here. And then here are some of the important terms. We talked about selectivity, and pressure ratio is straightforward, but cut is essentially the productivity of a stage. And we'll talk about trade-offs later on, but this is one of them. If you have a low cut, you're not really producing anything, but you aren't consuming much energy. If you have a really high cut, you're producing a lot, but you're consuming more energy because the concentration gradients change. The cut is theta. And then we'll switch gears a little bit. I want to talk about one really popular research topic in the field. Here's just a bunch of papers about something called the permeability selectivity trade-off in membrane separation. It comes up in gas permeation and desalination, every other field. So here's a little bit about that. So we talked about A and B, which is water permeability and salt permeability, or we can use R for desalination. We have alpha to correlate the selectivity of gas permeation. Well, actually, the alpha competes with flux, and A and B compete directly. And so I say zero sum because if you increase A, you produce more water per unit pressure. But by making water more permeable, you also make the salt more permeable because, I mean, there's no special membranes. If you make it easier to push one thing through, kind of pushes the other things through as well. And that same thing happens with gas permeation. So this is a plot from Robinson, the 90s, of showing this relationship. Now, this is for air separation. As we increase the permeability of oxygen, we actually decrease the selectivity of oxygen versus nitrogen. So maybe there's a sweet spot in the middle of where we have a decent permeability and a decent selectivity. But if we want a really, really selective membrane, has pretty much no permeability. You can imagine, I mean, anyone can make a membrane that's just a piece of steel. Oh yeah, separate 100% of the salt, but you're not really making anything. And then on the other side, I mean, I can make lots of water if I just push it through a coffee filter, but I'm not retaining any salt. This is for gas separation. This is what's going on in desalination. The same kind of linear relationship between rejection and permeance. Here's our coffee filter, and here is our piece of sheet metal. Okay, and I want to talk about some reasons for why separation systems will lose performance for membranes. One type is called fouling or biofouling, when a biological growth occurs on the surface of a membrane. And this will block the surface area, which will not allow diffusion through it, or it will, I mean, it can also damage the membrane. Concentration polarization. Oh, I guess fouling can also occur with, like, if you have proteins depositing inside the membrane and clogging pores. Concentration polarization we discussed earlier. If you have the boundary layer, you increase the concentration at the surface and you have a huge delta pi, then it's going to eat away at your operating costs because you need more applied pressure on this feed side in order to push the water through. Because osmotic pressure, water wants to go this way. Water wants to go this way. That's why it's called reverse osmosis. There's also scaling or precipitation, which looks just like this. If you have too much concentration at the surface, you can actually form a precipitate. And compaction is just what it sounds like. Pushing the membrane together with pressure will decrease the flux. And other degradation from pinholes or oxidation with like chlorine can cause loss of performance, forming holes or something like that. Can lose performance in selectivity as well as in flux. And I want to finish up by talking about industrial processes. And we have 3 different types of modules. There's the plate and frame modules, which are used in processes like electrodialysis. There's the spiral round modules, which are used very commonly in seawater desalination. And then, I mean, hollow fibers as well. And then here's how you pack a ton of surface area into a small volume with hollow fibers. And spiral wound membranes do that in the same way. But that is the 3 types of membrane modules. This is what a hollow fiber membrane looks like. Spiral wound membranes and like just the module in general are very, very interesting. But I could not explain it to you in under like 5-10 minutes. You can spend a whole hour talking about it. I definitely recommend reading about it because just the process design that goes into it is very neat. And then here I'm just showing the packing density is surface area per volume. Is there a question? Yeah. You could spend a whole class on this, but I'm trying to just distill it all into one day. So hopefully you're learning a lot. Packing density is area per volume. And so plate and frame is less optimal in that regard. But we need to use that type of setup for electrodialysis. And spiral wound is a little bit higher, and hollow fiber gives us the highest packing density. And yeah, just like we learned with adsorbents. And finally, this is what they look like at the industrial scale. So electrodialysis is actually used industrially to separate low salinity brackish water or something, or for the semiconductor industry to make ultra pure deionized water. So that's the plate and frame. And we've talked about spiral wound for seawater desalination. This is the Carlsbad plant. And then finally, here's ultrafiltration hollow fibers implemented in modules for the dairy industry. And I don't know exactly what they're doing here. Could be whey protein separation from milk or something like that. But yeah, that's what all of the processes we talked about look like when implemented at the industrial scale. So I think we're right on track for time, and that's it for today. There's a lot to pack into one session, but I remember spending multiple weeks on it. I mean, I've spent years on it. So if you're interested, I can definitely point you in the right direction. If you want to learn more, feel free to email me. The Cedar text is really good. Are any of you doing membrane separation for your final projects? I can definitely help you. But yeah, now I'll open up the floor for any questions. Oh, awesome. Just membranes in general, or are you looking for a specific process? Oh, neat. There's a lot of information out there. Well, let me know if you want some resources. I can share them with you. These are probably the most related processes to RO. There's lots of different types. All right, well, if there aren't any questions, I guess we can stop. I can stop sharing. Is there anything else you'd like to talk about, Dr. Josephson?
Well, let's thank James for sharing his presentation with us with lots and lots of knowledge and information. Yeah, last year in my class, we spent, I think, about 3 weeks on membranes as well. There's just so much to talk about. And so thanks for trying to condense some of these information here. If you guys have questions, feel free to reach out to us. The slides are on Blackboard. We will have some quiz questions on the membranes, but hopefully you had some fun, and we can, you can ask more detailed questions later.
I'll hang around until the end of class if you can ask questions.
Yeah. All right, well, thanks everyone.
Yeah, thanks guys. Thanks for having me. This was a great opportunity.
Thank you.